So, hello, my name is Leszek Orzechowski. I'm a team leader at SpaceSmall Student Design Team from Poland, and it's an honor to be here and be able to present our mission proposal. It's going to be something different this time. This is going to be a human-driven presentation, basically. But let me start from the beginning. We are a group of young engineers, and every one of us represents different field of knowledge and different view on space exploration. Each of us was responsible for different aspect of the mission. And so in order to keep it coherent throughout the design process, we focus around a common idea that is hidden inside our team's name. Space is more is a paraphrase of the words less is more, said by an architect, Mies van der Rohe. His goal was to design a living space, perfect for human needs, not only physiological, but also psychological. His works were coherent in form, function, and construction, and inspired many generations of architects. Thanks to his work, the living space became more human, and we believe the same must happen in outer space. In other words, our name stands for creating a space habitat best suited for humans. Our purpose was to design a space mission that was supposed to be simple, safe, and affordable. Safe in terms of a mission not only means a spacecraft design that will endure 1.5-year mission, but also a place when crew can live in a good health and comfort. We tried to find a solution to give the crew as much living space as it can get. To do that, we focused on the idea from the 1960s called wet workshop, proposed for Skylab 2 mission. It assumed using an empty fuel tank of the Apollo stage rocket and adjusting it for human needs. Unfortunately, it was also proposed to utilize it with rigid partitions and heavy science equipment that needed to be sent into orbit. As a result, this idea quickly became too complicated and expensive, and soon after was abandoned. With our work, we wanted to redesign giving idea, making it possible and accessible in the 21st century. And at the same time, we wanted to introduce novel ideas, changing the way of thinking about human occurrence in the space. Our mission involves the use of 2 rockets. Whoa. Okay, there was supposed to be rockets here. But yeah, SLS and Falcon Heavy. Yeah. SLS payload is its own modified large upper stage. It has extended liquid oxygen and liquid hydrogen tanks. It also is equipped with an adapter that was designed for docking with the rest of the ship and redirecting any forces that could normally affect liquid hydrogen tanks for dome. It's also equipped with an adapter. Airlock that is similar to those used in space shuttles. It protects NASA docking systems and its sensor packs from cryogenic environment present in hydrogen tank before our Mars injection burn. Inside of airlock, there is also a drone designed by our team that will be put in use in the right time of the mission. From the airlock and the NASA docking system, there are 6 ducts led inside of wet workshop or extended liquid hydrogen tank. These are thin-walled steel pipes that protects installation ducts from cryogenic environment. The last addition to liquid hydrogen tank are snap hooks on the tank's inner walls that making the way we decided to utilize its interior, but I am not going to spoil it just yet, and we will go back to this topic soon enough. But for now, let us focus on Falcon's heavy payload. It carries a stock of dry workshop pressurized module, Cygnus service module, and Earth reentry pod, and also a launch abort system. Yeah, this is important to find out. Dry workshop is a mission systems module that is an integral part of the wet workshop concept. We based its construction on Leonardo Permanent Multipurpose Module docked to ESS. Therefore, it's protected from outside environment with multi-layer isolation, micrometeoroid and orbital debris protection, and aluminium-lithium shell that also provides radiation shielding. At the exterior of dry workshop, there is a 1.3 meter high-gain antenna that is based on the construction of a 2001 Mars Odyssey orbiter antenna. It uses Deep Space Network and operates in X-band, while its low-gain antennas operates in S-band. This system provides connection with the on-ground team and allows for multiple system checks and sending low-resolution videos. You can also see radiators that are part of our environmental control and life support system. SELSS is the most reliable, tested, and ready-to-apply system used with great success on International Space Station. SELSS was placed with high proximity to hygiene compartment for ease redirecting of used water. This closed-loop system has efficiency coming up to 88% of water recovery and 98% of oxygen recovery. Air is directed into wet workshop through pump system, through NASA docking system. We calculated that 500-day mission for two will require 2 tons of water, 1 ton of food supply, and 1 ton of gases. All of above systems were taken into consideration in our project as existing, verified, and ready-to-use devices. Ending the wet workshops topic, it's important to point out that it also yields other mission supplies, including zero-G 3D printer for simple onboard repairs, materials needed to utilize wet workshop, interior and unassembled training equipment. As it goes for re-entry pod, it is the same capsule presented by Inspiration Mars Foundation in their mission proposal. It is a scaled-down Orion capsule. The diameter was reduced by 20% of the original Orion, which decreased weight by 40%, and as a result, giving 5.5 tons with fuel included. It's connected to Cygnus service module by an adapter. And Cygnus service module is slightly larger than its basic version. It has increased hydrazine tank and is equipped with 80K ultraflex solar panels that can be scaled in order to meet mission expectations when it comes to power needed. But before we proceed to space launches, it's important to mention about radiation shielding during our mission. We can, according to materials provided by Mars Society, we estimated that overall radiation dose absorbed by our crew during our mission will increase probability of lethal cancer by 1.4 percentage points when it goes to for galactic cosmic rays, and as it goes for special solar particle events, they can be almost entirely shielded by orienting spacecraft with its longer axis toward the sun. Also, water supply can provide additional protection from solar particle events as astronauts can hide behind it. Now we can proceed to space launches. Mission starts with the launch of SLS. Its payload, extended LUS, will be put to low Earth orbit and will wait there for a couple of days. The next launch is Falcon Heavy. After its payload being put on LEO phasing orbit at the same plane as extended LUS, Earth reentry pod and system module will jettison from rocket and dry workshop, and then perform rotation maneuver. After that, it will proceed to dock with dry workshop, and after hot stack will jettison from the rocket and make a correction burn to meet with extended LUS. After confirmed docking, our spaceship is complete, and we will perform the first burn that will put it on highly eccentric 5-hour period orbit. And after the second burn, we'll put our spacecraft on a free return trajectory. It is worth to mention that we are not only using trajectory proposed by Exploration Mars, but we also made a bold attempt to recreate it using our own algorithm, and came out with a very similar yet different trajectory that uses less C3, allows free return, and is still within a margin of 14.2 kilometers per second re-entry speed. We also estimated and not only estimated but simulated Venus Mars flyby trajectory for 2021. But using trajectory for 2018, we managed to get the 80% mass margin that allows for a lot of modification in our design. We can afford to take on board additional radiation shielding, spare life support system, or even begin dry workshop module or different re-entry point. Here you can see trajectory for 2021. And now we are on the we are now on our free return trajectory, and there is no going back. Any corrections in our trajectory will be performed by a hyperbolic engine on service module, and any orientation corrections will be performed by RCS engines on service module, which include keeping spacecraft based with its longer axis for the sound, and also to rotate it to ensure visual of Mars flyby. But to see the red planet, the crew will have to utilize and to assemble wet workshop. To do that, they will have to get rid of the rest of the fuel. To get rid of the rest of the fuel, the liquid hydrogen tank is going to be exposed to space vacuum. Okay. And after, it will be treated with nitrogen from our life support system. After that, hatch at the far end of our airlock opens and provides unobscured way for our drone to scout the interior. When the sensor packs, both in airlock and on drone, proves that the environment, that the interior is safe to enter, the crew will install lights and ventilation units. We try to do our best to create a living space that has a great volume, is cheap and simple to utilize. To do that, we have taken an inspiration from art and architecture from 1960s, which is the same period as wet workshop idea. Here you can see a work of minimalist painter Mondrian. He created a lot of compositions using lines and rectangles that in his language meant relations between a man and a woman, which is quite complicated. But some architects took it even further, and by adding third dimension, created architecture. We used this idea to create a living space inside of wet workshop. We used sheets of fabric stretched between iron rods, and that create floors, walls, and tabletops. These are PCV-coated membranes that became rigid when stretched. The rolls of membrane, coiled in dry workshop take up little space and have a small wave. But in wet workshop, when they are fixed to iron rods that also provide communication systems, they give us a space with huge compositional and functional potential. Here you can see a living space. We decided to create a living space that resembles the ones on Earth, with living room, bedroom, and private studies, only because this should help crew to identify the new home that they will spend there like a year and a half. On the opposite of the main membrane, there is a place, a workspace for workout and science purposes. The study will contain tabletops with plexiglass terrariums for research into cultivation of algae in space. The mission have enough food supplies for all its duration, yet to provide healthier and fresh meals, the crew will test usage of spirulina algae. To do that, they will use a device called Spiru. Spiru is the world's first bioreactor for the home cultivation of spirulina, and was designed by Polish design group and Polish engineers. Spiru has already proven itself in providing meals rich in vitamins, proteins, and unsaturated fatty acids. But to stay in shape, they will also have to train a lot. There is some usual training equipment like treadmill or training ramps that crew can work with, but the great volume provided by a wet workshop led us to design a centrifuge, or what that we call G-bike. Microgravity negatively affects bone tissue. Experience shows that astronauts lose some 1 to 3% of bone tissue after a month spent in orbit. We decided to create an artificial gravitation force using centrifugal force. The G-bike is designed for 2 people that use their legs to spin the device, just like a normal bike. The angular momentum derived from G-bike should be equal to 0. That's why we need to use 2 bikes with equal mass that spins in opposite directions. Centrifugal force will be equal to 1.2 Gs at user's feet level, and overall force stimulation will help to compensate negative effects of weightlessness on human health. To avoid dizziness, the crew will use virtual reality goggles like Oculus Rift that will project vision of a bike ride in a pleasant environment. Training schedule is included in a daily routine that you can find in our project. I don't know whether it's on your desks or not. Doesn't matter. It shows crews daily tasks during their 501 days flight. That includes scientific work, training sessions, and meals and free time. After spending over 500 days in space, the crew will begin the re-entry phase by rigid stunning Earth re-entry pod and the service module from the rest of the ship a few hours before landing, and perform necessary corrections using RCS engines. Then, the service module will be decoupled from Earth re-entry pod, allowing the crew for the direct re-entry. Mission ends. The cost of the mission largely depends on final prices of both SLS and Falcon Heavy launch prices. But we can claim for sure that utilizing empty fuel tanks greatly cut the costs of the mission, as we don't have to launch additional habitat for the crew. Other costs we could predict more easily, like using Deep Space Network or costs of other equipment on board. And taking all of them into account, we managed to design a space mission that is not only cheap, but also offers a great value for the price of $1 billion without launches, development, and so on. This concludes our mission proposal that emphasizes on creating a safe and comfortable living space for future pioneers. Thanks to our inspiration with art and architecture, we could redesign with workshop concept that can provide large space that is cheap, easy to utilize, and friendly for users. It also allowed us to design a G-bike that can compensate one of the greatest threats, which is negative effect of lack of gravity on human health. With our slightly modified inspiration mass trajectory, we can address any structure or supply issue due to our 80% mass margin, which is crucial because every mission tends to put on weight during the development process. Well, good designs work, and they saw a lot of good designs. Great designs not only work, but are coherent in form, structure, and function. They can give to user even by using simplest means. If you could imagine a TV commercial of such a mission, well, maybe not imagine because I'm going to show you. It starts with a question: what would you do living? What would you miss living Earth? And do you have to miss anything? And as you take off your VR goggles, you find yourself in a vast space that is your home. And we provide over 360 cubic meters of space. We provide unique training equipment that will keep you healthy. And as you approach Airlock to go to drive workshop, you are going to see your purpose of going on this trip. After spending 247 days, you finally reach Mars. And it doesn't necessarily have to be unpleasant trip. In fact, it could be very friendly, pioneer-friendly trip. Thank you very much. Oh, and it's worth to mention our sponsors, since we made it like a crowdfunding campaign to came here. They are very nice people, all of them. So, we're waiting for questions.
Did you consider what modifications you would need to make in order to be able to do this on a single launch?
Simon?
In order to do it in a single launch, we had to get rid of the cargo module that would provide the crew with the life support systems and things to put inside the wet workshop after we launch. So the SLS block tool can provide you only with the fuel for our mission.
How much delta V does that service module have? Can you use that to cut down the re-entry velocity of the capsule shortly before it enters Earth, before you discard it?
We estimated that the 900 kilos of the hydrazine can provide the whole craft with 200 meters of delta V, but we didn't count the delta V of the only capsule and the service modules. So it could be sufficient to provide a couple hundred meters of delta V.
How much propellant is it?
900 kilos.
Okay.
What were your assumptions about the Earth return velocity? I know you used a modified Orion there, but can you say a little more about it?
We just focused on the fact that we had a constraint on the 1,400 kilometers per second. So this is what we stick to during the trajectory planning. However, the 2021 trajectory leaves us with the 200 kilometers per second entry velocity. So this could be also a factor when taking into account that not every rocket can be, the SLS Block 2 might not be ready for the 2018 mission. So the 2021 trajectory is also very good for us.
And we also calculated trajectory that focuses on reducing re-entry speeds, so we can get on that very quickly. Okay. Here's our trajectory that uses a minimum C3, and as you can see, and here is our trajectory with higher margin, but well, trajectory optimized for Earth re-entry velocity is 13.7.
Right, okay. That's consistent.
You also look at the 2-year return?
Yes, Mars, Venus trajectory. There's also alternative 730-day plus trajectory, but it's not worth mentioning.
Why isn't it worth mentioning?
Because the person that was responsible for calculating it is unfortunately absent. So I strongly suggest and recommend reading it in our report. Okay, so Venus Mars flyby trajectory uses Malopoulos C3 as entry velocity of 12.7. Flyby distance with Venus is like 10,000 kilometers, and flyby on Mars distance is 100 kilometers. Any questions?
All right, thank you very much.
Thank you very much.